again, year 12. Going to be interrupted by the sound of my cat eating over there. I don't know whether we should pause and start again. Let's carry on. So, time for another thing. I put out of the year 12 course, yield and atom economy. To put the two things together could be a disaster because people get the two things mixed up. They are obviously not the same, but they're also very different in the way that they're trying to express something about some chemistry. So yield, completely based on doing some chemistry with chemicals, getting them out, putting them in a container and doing whatever you need to do to get them to turn into products. Yield is about how successful you were as a percentage at getting the maximum amount. But you won't get 100%, you'll lose some. Therefore, hence the statement underneath, only from experiments with chemicals. So you cannot do a yield without getting some chemicals out and actually doing the practical. And it is a percentage success rate, so it's the collected amount. And I've used the word amount because it could be, you could do the calculation moles, could be grams. You can do the calculation with either, it comes out the same, so the collected amount either in grams or moles, theoretical maximum amount in the same units, times 100%, done. Atom economy doesn't involve you getting the chemicals off the shelf and doing anything with them. It just involves looking at the balanced equation. Now in a lot of textbooks they go formula mass of the product that you're trying to get divided by the formula masses of all of the reactants including their balancing numbers. I don't see the point in that because that means you've got to work out more things. All you need to do to get it right is the mass that you wanted, now this is formula mass, over the total mass of all of the products, which includes the one you've just calculated, saves a bit of time, times 100. So this is where the confusion comes because they're both expressed as a percentage. So AE, atom economy, formula mass of the product times its balancing number, which may be 1, but it might not be. And then it's the total formula mass of all of the products, but you've got to include their balancing numbers in that calculation as well. Times 100 to get it as a percentage. But it only comes from the balanced equation. You literally get the balanced equation, you can do it. Now there is one trick with it, that if you've only got one product, really important thing, if you've only got one product, the atom economy will by default be 100% because you haven't got anything else. In another equation there will be the product that you want and there'll be some other stuff. Nominally that is probably not going to be thrown into the environment unless it's carbon dioxide or water, but it is wasted mass, hence the term atom economy, because it's how many atoms you conserve into a more financially suitable product for sale against how many you don't want. The reality is companies have waste streams that make money out of whatever they can out of. Even carbon dioxide gets sold to the drinks industry to make fizzy pop stuff. So, only from the balanced equation, like I said, don't need to get the chemicals out, just need to look at a balanced equation. And the thing I'm going to write down here is that they are not related. Now I don't mean that they're completely unrelated, because obviously if you've got an equation that you've got to do both to, there's that they have in common. But the value for that is not dependent on the value for that, or vice versa. So they're very much independent concepts around a reaction. I'm going to do a couple of examples, well, I'll do 3 examples actually, and then set you free on the examples that come with the video. But I need to get the board ready for the first example. I'll see you in a moment. Okay, so first example, making hydrogen from methane and water. Well, water as steam. So there's the equation, and I've now got one of my cats chasing its tail. Goodness. So you want the atom economy, it's hydrogen we want, 3 H2s come to 6. That's 3 times the atomic mass of hydrogen, or the MR of hydrogen, whatever you fancy. All of it together, 6 for that, 28 for that, and therefore the whole thing is 6 over 34 times 100, 17.6%. Pretty poor atom economy. That's because most of the mass is in there, not in there, because of the light weight of a hydrogen atom. So atom economy 17.6%. To do a yield calculation you need to be told different things. You need to be told how much you're starting with and something about how much you've manufactured in the process if you're going to calculate a yield. If you're doing an experiment, that amount is the amount you measure from your dried finished material that you're manufacturing in a process. Usually organic, but doesn't have to be. So, like I say, you need that. I've set it up with 16 tonnes of methane and an excess of steam. Now when you've got this kind of question, you do have to consider which is the limiting reagent. Now when there's an excess, obviously the limiting reagent is the one that's not in excess, so it's nice and straightforward. In this case it's the methane that controls in terms of it's limiting how much you can make. So the limiting reagent determines how much product you potentially could get. That's the theoretical maximum. And it says here in this question that I've made up that you got 3.6 tonnes of hydrogen as a product. So just running through just what we've got here. Now it's in tonnes. Oh, here's a little thing. Really, tonnes are not what you do and calculate moles from, but because of the way tonnes are related to grams, I just think you can ignore the tonne thing. The only time you have to remember that you're working in tonnes is if you have to create a mass, then you have to not call it grams at the end because we've been working in tonnes. So I've called it equivalent moles. So formula mass of methane is 16, so that's 16 tonnes over 16 is equivalent to 1 mole. It's technically 1 megamole, a million moles. A far too big a number to think about. And then hydrogen, 2. So 3.6 tonnes made over 2, 1.8 mole equivalent. Now then you get to the thing of, do you work in moles, do you work in grams? It matters not. I kind of think you should be familiar with both, because often you start doing a calculation, you end up going down the moles route or you go down the grams route. In the end it doesn't matter because they give you the same answer. But if you wanted to go down the moles route, the maximum you could have got from 1 mole of methane equivalent is 3 moles of hydrogen. So it's 1.8 out of 3 as a percentage, 60%, 60.0, 60%. No, 60% because it was 16 tonnes without a decimal point. Significant figures. And then if you want to go down the grams route, it's on this side here. So you could have made 6 tonnes because you could have made from 1 mole, you could have made 3. So you do have to get into the moles thing, you can't avoid the moles as part of it. Just depends which one you calculate the yield with. And that would be the equivalent of 6 tonnes maximum of hydrogen. Yeah. So 3.6 made, 6 tonnes potential maximum as a percentage at 60%, same answer. Oh, there we are. So they're nowhere near each other in terms of value because they're not related, like I said just now. 17.6% representing the fact that an awful lot of carbon monoxide, in itself an issue because you don't want to be chucking tonnes and tonnes of carbon monoxide into the atmosphere. So they would have to manage that. Ideally they'd find a way not to release it into the environment at all in any form. And here we have a yield of 60%, which is how successful the process has been at converting methane into hydrogen, rather than how much you keep and how much you throw away, which is up here. Different things. I'm going to do another example, and we're going to do a thing where it's turned inside out. But I need to get the board ready. See you in a moment. So here's a second example, a little bit more, marginally more complicated than the first one. Also does another one of my things that I like to do, which is feature an element that never gets a look in at A level. In this case, it's the extraction of the metal Holmium. No, I know nothing about Holmium either, but it doesn't mean we can't do its extraction from a chemical equation. Here's the equation. The apparent method that you can use, although it's not the only method, is to take holmium chloride, HOCl3, and react it with calcium, and you extract out of it holmium and form calcium chloride. So if you're doing this to extract the metal holmium, this is not wanted. So here is the desired material from the equation. So the atom economy, based purely upon the equation, like we've been saying, we want 2 times holmium's. Holmium has a formula mass of 164.9 there. So we get 329.8, and the calcium chloride times 3 is 3 lots of there, 663.1. So the atom economy comes out as 49.7 by virtue of these calculations we've been doing. So less than 50% of the reactants gets turned into the saleable product, which is the holmium metal, which is much more valuable than calcium chloride. There we go. So when it comes to yield, which is here, yet again we can do it by moles and we can do it by mass, but in the end you still got to do a bit of moles in it anyway. And the setup here is a 1.764 kilograms of holmium chloride, which is apparently a lovely pastel colour, was reacted with an excess of calcium. So yet again the limiting reagent is the, well, to be honest, expensive material, which is the holmium chloride, and the product of holmium comes out as, in this question, 772 grams. So you're going to need the formula mass of holmium chloride, which is 271.4. I tend to do it by simple juggling of what I know. 164.9, 2 chlorines are 71, another one is 35.5, I think it's 20 all up. And the number of moles is therefore here 6.4996. Overworking the number of significant figures because you round it at the end. You don't want to keep rounding it because you'll round it outside the limits of where you can be. You can still get marks in an exam question, that is. So that's the number of moles of holmium chloride. In that equation it's 2 to 2, which is why it says 2 to 2 there. It's 2 holmium chlorides to 2 holmium, so the number of moles of holmium metal released is the same as the number of moles of holmium chloride. How many moles did we actually produce? We had 772 grams of holmium, which is 164.9 because it is just the element holmium, and it's 4.6816 moles again over doing the significant figures. So therefore the yield comes out, that's what you got, that's the maximum you could have achieved, 72% achieved. You can do it also by mass. Here's the mass version. You need to know how heavy your, or what mass your 6.4996 moles would have of holmium, and it's there, 1071.8, and you do the yield calculation, and of course it comes out the same because that's one of the things that happens. And there we have it. Now the next example will turn it inside out and go, how much will we get, because this process has a yield of, which is the other type of question you could get asked. But I need to get the board ready for that, so I'll see you in just a moment. So last example, like I said, turned around the other way, got a yield. Yield is quite a low yield of 18.5% for reacting silicon with nitrogen. What mass of silicon nitride, Si3N4 over there, would be expected if you use 2 grams of silicon and 1.5 grams of nitrogen? Now here, you don't know the limiting reagent. So you need to work out which one of these is controlling how much you get and which one there's more than you need. And so therefore, there would be some left over. 2 grams divided by 28.1, 0.071 there, that moles of silicon. Here's the number of moles of N2. Then you need to look at the balancing, 3 to 2. So there are 2/3 the number of moles of nitrogen required than there are moles of silicon, because it's 3 to 2. So you would do that times 2/3. There's the number of moles of nitrogen that would react with 2 grams of silicon. Got that? That is less than this, So there's more nitrogen than you need to react with the amount of silicon that you've got, because when you look at the number of moles, you would only need 0.474, you've got more than that. So therefore it's this number of moles that is limiting how much silicon nitride here you get. So you need to look at how many moles of this you made. I just rubbed out part of the 3, and because it's 3 to 1 because of the formula, you divide that by 3. There's the number of moles of silicon nitride that you make. The max, that's the, this is the 100%, didn't do 18.5% yield to do that, and that comes at the end. So this is the mass of silicon nitride that you could have got at 100%. So here it is. This will be the formula mass calculation for Si3N4. And you get 3.3286 grams maximum. Then you go, that's the 100% yield. I actually was working at 18.5, so you multiply this mass by 18.5 over 100, which is 0.185, which is what this is here, and you get 0.616 grams. So if you just look at that process, limiting reagent determination followed by using the one that limits to find out how much silicon nitride you would have made at 100% yield, turn that into the number of grams you would have made, and then do the reduction to 18.5% of the maximum 100% amount. And there it is. They're attached to some further questions to do, lots of further questions I've got for you. You should be having a go. The answers are in there with them, so you know whether you got them right or not. Obviously the point of them is not to just go straight to the answers, but you know that because you're trying to learn these things. And I'll probably see you very soon for some other part of chemistry very related to what you're currently doing. I'll see you soon. Bye bye.